Optimization problems are some of the most elegant uses of calculus that you see in the entire course. And we're essentially trying to use our techniques for finding maxima and minima to optimize some kind of real-world situation, such as minimizing the material required for a box. But using calculus on these optimization problems can really yield some insightful results. So let's try one out. This one says maximum area rectangles, and it asks, of all rectangles with a fixed perimeter P, which one has the maximum area? Give the dimensions in terms of P. Okay, well, there are some steps, or at least some guidelines for optimization, so let's take a look at these guidelines, and we'll follow them somewhat. These guidelines are more suggestions for these kinds of problems because they can often be overkill. Okay, so here are the guidelines. And again, wear these like a loose-fitting garment, right? These are not meant to be a very strict, like you have to do it step by step. You'll develop an intuitive feel for these optimization problems and more or less discard these guidelines after working several problems. So use these as a way to get started, but this is not meant to constrain you to the point of heavily relying on these guidelines, right? You want to develop a feel for how to approach these problems rather than incessantly and restrictively referring to the step-by-step process. But we'll start with the step-by-step process. Step 1 says read the problem carefully, identify the variables, and organize the given information with a picture. Okay, you do always want to draw a picture when you can. That is a definite thing. I'm always surprised at how many people try to solve optimization problems and related rates too without drawing pictures, and it's very hard to get started without a picture. Okay, so we have a rectangle. Let's call these dimensions x and y. And then we have our area, which is what we're trying to optimize, x times y. So let's write that as our goal. And I'm already getting ahead of the steps, so we'll go back to those. Goal, maximize the area. Maximize the area, and you always want to identify your goal so you don't get lost in the woods and calculate the wrong thing. Okay, back to our steps. Okay, for step 2, we want to find the function we want to optimize. So the function to be optimized, we did that. In our case, it's the area. We call that the objective function. But you'll very quickly identify which function you actually want to find the maximum or the minimum of. We call that the objective function, and you write it in terms of the variables of the problem. We've already done that. We decided that the objective function was a, and we wrote it in terms of x and y. And that's generally how these will go. You'll have some objective function, you'll have a couple variables that you can write it in terms of. On to step 3, identify the constraint. You'll be given some other piece of information that limits our objective function. So you want to search the given problem for that constraint, and then you want to write that out as well. Write them in terms of the variables of the problem. And then step 4, use the constraints to eliminate all but one. So essentially only one variable. Eliminate all but one independent variable of the objective function. So we want to have the objective function only in terms of one variable. Well, here we have two variables, so we have to get x in terms of y or y in terms of x. So let's see if we can do that. So we have our objective function, a equals xy, and our constraint. Well, here's our constraint, a fixed perimeter P. So sometimes it's subtle like that, but it's always in there. Well, how's that a constraint? Well, we can at least write it out in a way that's more recognizable mathematically. P equals 2x plus 2y. That should be a formula that you recognize from somewhere back in geometry land. And remember, our goal is to get this area in terms of only one variable. So let's see if we can solve that constraint. Let's solve that for y. Remember, now p is a constant, right? How do I know it's a constant? Well, it says fixed perimeter p. So that tells me that p is some fixed number. We're just going to leave it in terms of p, but it could be 5, it could be anything here. So let's solve for y in terms of p. So we have 2y equals p minus 2x. Solving that for y gives y equals p minus 2x all over 2. And the good news is we can now plug that in up here to get this whole area equation in terms of one variable, x. So I plug that in and get area equals x times p minus 2x over 2. Back to our guidelines. On to steps 5 and 6. Step 5, with the objective function expressed in terms of a single variable, we have that. Find the interval of interest for that variable. The extent to which this interval of interest is necessary is questionable. Oftentimes you don't really need that, but we'll do it in this case. But most problems you can kind of skip this and everything's going to be fine. But I suppose it helps to think about it from time to time. Okay, step 6. Use methods of calculus to find the absolute maximum or minimum value of the objective function on the interval of interest. Okay, so that method of calculus is going to be the derivative and setting it equal to 0. Sometimes you have to do a little bit of work to determine whether or not it's a maximum or minimum, but usually it's pretty clear that the thing that you've computed is the thing that you want. And if necessary, check the endpoints. So every once in a while you'll end up with a situation where you need to check some endpoints. Okay, let's go back to our exercise. So our interval of interest is what? X is going to go from what to what? And, is it useful to think about this? Well, maybe. Let's see. Well, what's the smallest thing X could be to the point where it's absurd? Let's say 0, and I'm going to leave it open because if we have X equals 0, then the whole thing collapses. So I'm going to do an open interval from 0 to, and it would be, again, absurd for it to be 0, and then p over 2 is another one, right? Then it's just half the perimeter is X. So if X was p over 2, that would collapse our entire rectangle again, and we have basically just one very long, flat nothingness. And we have to ask, was it useful to really think about those? Maybe, maybe not. Let's move on with our derivative. We have our area function here, and we want to take the derivative of that. But first I'm going to fix it up a little bit to make it easier to take the derivative without having to use the product rule. What if I wrote this as, how about this? I'm just going to do a little bit of algebra. P over 2x minus x squared. Right? I'm just messing with the algebra just a little bit to get it into a nice differentiable form. Now we're ready for our derivative. Take the derivative, set it equal to 0, find the maximum. Okay, p over 2 minus 2x, which we can quickly set equal to 0. Well, that gives 2x equals p over 2, or x equals p over 4. Well, we know that it's not a minimum because these two things are the minimum. So I guess it does help to have an idea of what the minimums for this function would be. So this must be the maximum. X equals p over 4 is the max. So you can do a little bit of reasoning like that. And just to be safe, to ensure that this is a maximum, we could also look at the second derivative test. Note that a double prime would be -2. Running out of room here. Which is concave down, which means that any critical point in here is going to be a maximum. Okay, that's a good way of looking at it. So you can use that second derivative test. So go back and review that. But it tells us that if a function is concave down and you have a critical point, that critical point is a maximum. Okay, so what does this tell us? One of the cool things about these problems is interpreting the result. We have x equals p over 4. So let's plug that in here for x. So p over 4 goes in here and see if we can compute y. That gives us p equals 2 times p over 4 plus 2y. So let's see here. How about this becomes p over 2. Subtract off p over 2. We get p over 2 equals 2y. And divide by 2. Look at that. P over 4 equals y. Huh. So those are our dimensions. It's p over 4 by p over 4. And that's our final answer. P over 4 by p over 4. What kind of shape is that? It's a square. And that's the deep part that comes out of this kind of exercise. We've determined that the maximum area of a rectangle, given a fixed perimeter, is always going to be a square. And that's a pretty deep result, right? Without calculus, we'd be hard-pressed to prove that that's the case. But with a little bit of calculus and a little bit of computation, we very quickly arrive at a very general result that has very broad implications. Let's try another one. Okay, so here we have the minimum sum, and it says to find positive numbers x and y satisfying the equation xy equals 12 such that the sum 2x plus y is as small as possible. Well, one of the first things we can do is contemplate how hard this would be to do without calculus, right? We want positive numbers, so I'm thinking that means not 0, and we want to make this sum as small as possible. Well, what if we just made them 0.1 and 0.1? That's pretty small. Well, then that doesn't satisfy x times y equals 12. Well, 4 and 3, would that do it? 6 and 2? Do they have to be integers? What if we had some kind of rad something? And how would we go about finding that? So maybe try some numbers and think about how challenging this would be to solve without using calculus, and then we'll use the calculus to solve it. Okay, we need to identify our objective function and our constraint. The objective function is the thing that we want to maximize or minimize, and this is it here, the 2x plus y. It says we want it as small as possible. So I write that as the goal. I like to be very clear in what I'm doing, goal. I want to minimize the function 2x plus y. Let's call it s for sum. S equals 2x plus y. And then what's our constraint? Well, our constraint will always be the other thing given in the equation, xy equals 12 in this case. Okay, note that I'm not even going back to the guidelines. I'm just going to use the very intuitive approach now and solve this thing out. Well, we want our objective function in terms of only one variable, but we have two variables. So then we say, okay, let's go over to our constraint and solve that so we get one variable in terms of the other. I will solve this for y and get y equals 12 over x. And then we take that y and plug it in over here in our objective function. Boop. That gives us s equals 2x plus 12 over x. And voila, we have our objective function in terms of one variable. We want to minimize it, so I'm going to take the derivative, I'm going to find the critical points, and I'm going to think more about it. So our derivative here is then s prime equals, well, derivative of 2x is 2. The derivative of 12 over x is minus 12 over x squared. And if you're saying, how did you get that? Just write this as 12x to the minus 1 and use the power rule. That's where it came from. Okay, well, this is undefined at x equals 0, but that's not going to be an option for us because we're looking at positive numbers. So let's ditch the x equals 0 case and set this whole derivative equal to 0 and solve for x to get the other critical point. So we have 2 equals 12 over x squared. And solving for x, bring that up and divide by 2. We have x squared equals 6. So x is plus or minus rad 6, but I'm only taking the positive case. Why? Well, look, it says we're only dealing with positive numbers, x and y. So I'm not going to take the negative rad 6. I'll just stick with the positive rad 6. Okay, so there's one of our numbers, rad 6. I wouldn't have guessed that. That's for sure. How do we get the other number? Well, you take the rad 6 and plug in over here for x and solve for y. So that gives us 12 over rad 6. Rad 6. Well, that's nice, but let's fix this up a little bit. I'm going to rationalize the denominator by multiplying rad 6 over rad 6. So that gives us 12 rad 6 over 6. And we can write that as 2 rad 6. So our final answer for these two numbers is rad 6 and 2 rad 6. I argued that that's a pretty incredible result, especially considering how easy it was for us to get it. Now, it's not completely trivial. We had to do some calculus. But to me, it's always surprising just how challenging this would have been to solve this without using calculus and how straightforward it is with calculus. So we've really come a long way in developing some very powerful tools that can be used to solve things and give some very useful results.